Good morning, everyone. So, welcome to my YouTube channel. So, today we are going to see 30th lecture on Riemann integration. Today we learn what is Riemann-Lebesgue Lemma. Okay. So, Riemann-Lebesgue Lemma. Let f belongs to RAB. It means f is Riemann integrable function. Then limit n tending to infinity a to b fx cos nx dx is equal to 0 and limit n tending to infinity a to b fx sin nx dx is equal to 0. This is Riemann-Lebesgue lemma. So we will prove it. Okay. Since sin nx and cos nx are continuous functions, okay, so this implies sin nx and cos nx are Riemann integrable because every continuous function is Riemann integrable. Okay. F function belongs to the RAB. It means f is Riemann integrable. Now, f sin nx, cos nx are Riemann integrable. We get f x cos nx function is Riemann integrable and fx sin nx function is Riemann integrable. Okay. So we get both the functions are Riemann integral. That is why we can talk about their integration. That is Riemann integral. Okay. We'll show that this Riemann integral tends to 0 as n tending to infinity. Okay. Therefore, for each n belongs to n, the integrals a to b fx cos nx dx and a to b fx sin nx dx are well defined because the inside integrand is Riemann integrable. Okay, this function fx cos nx, fx sin nx. Okay, so these integrals are well defined. We are to show that these functions this integral tends to 0 as n tending to. Okay, for each n belongs to n. So we get these two for. Okay, so we get that these functions are Riemann integrable or n belongs to n. Okay. Now we consider a partition. Since as F belongs to R, A, G, okay, choose a partition P is equal to A x0, x1, x2 up to x xl is equal to B. Okay, such that UPF minus LPF is equal to summation I goes to 1 to n capital Mi minus small mi delta xi is strictly less than epsilon by 2. So I am writing here let epsilon greater than 0. So given epsilon greater than 0. So let epsilon greater than 0. Let epsilon greater than 0. As F belongs to R, A, B, it means F is Riemann integrable. Choose a partition such that this happens. Because function is Riemann integral. Okay, it will such partition will exist. Okay, no problem. So put In is equal to A to B fx cos nx dx. So this integral can be written as summation I goes to 1 to L xi minus 1 to xi fx cos nx dx. Okay. So we have put this, then In is equal to this one. Okay. In is equal to this one. So I can add I is equal to 1 to L xi minus 1 to xi. I can add and subtract. Okay. I can add and subtract fxi minus 1. Okay. Then both I will get. Cos nx dx. So this is equal to summation I goes to 1 to L xi minus 1 to xi fx minus fxi minus 1, okay, cos nx plus summation I goes to 1 to n, sorry, L, L fxi minus 1 cos nx dx. So this is some integral also is here. Integral is also here. Let me write it. Integral xi minus 1 to xi fxi minus 1 cos nx dx. Okay. So what we got? So this implies In will be less than equal to. So this will imply, so I'm writing directly there. So this will be less than equal to. So this will imply In will be less than equal to summation I goes to 1 to L fxi minus 1 to xi fx minus fxi minus 1 cos nx. Okay. So this is a constant. It will come out. Summation I goes to 1 to L fxi minus 1 summation. So this is absolute value here is xi minus 1 to xi. Okay. Cos nx dx. So this is absolute value. Okay. Now cos nx is less than equal to 1, but this is less than equal to summation I goes to L xi minus 1 to xi fx minus fxi minus 1. Because absolute value of cos nx is less than equal to 1. Okay. Okay. So what is this? So summation I goes to 1 to L, and this is this integral. Fxi minus 1 xi minus 1 to xi cos nx dx. So this implies In. Okay. What is this? So we got this one. Let's say it equation number 2. Now, what is this? Xi minus 1 to Xi Fx we know that Fx minus Fxi minus 1 will be less than equal to supremum of Fx minus Fy such that Xy belongs to Xi minus 1 to Xi. But this is nothing but Mi minus this. Okay. This implies Xi minus 1 to Xi Fx. Okay. Minus Fxi minus 1. Okay. Dx. This is less than equal to Xi minus 1 to Xi. Mi minus small mi dx. Okay. So what is this? This is equal to mi minus small mi Xi minus Xi minus 1. This is mi minus mi. What is this? This is delta Xi. So this implies, okay. So this implies Xi minus 1 to Xi Fx minus Fxi minus 1 dx is less than equal to capital Mi minus small mi delta Xi for I goes to 1 to up to L. So this implies summation I goes to 1 to L Xi minus 1 to Xi. Okay. Fx minus Fxi minus 1 is less than equal to summation I goes to 1 to L Mi minus mi delta Xi, which is less than epsilon by 2 from 1. Okay. So this implies summation I goes to 1 to L Xi minus 1 to Xi Fx minus Fxi minus 1 dx is less than epsilon by 2. Okay, let's say this equation number 2. Next, what is xi minus 1 xi cos nx dx? This is nothing but sin nx upon n, sin nx upon n, xi minus 1 to xi. Okay. So what is this? This is 1 upon n sin n xi minus sin n xi minus 1. Okay. So this implies absolute value of this integral cos nx dx, that is less than equal to 1 upon n sin n xi plus sin n xi minus 1. Okay. I minus 1. Okay. But sin is always less than equal to 1. So this is 1 plus 1. Okay. So this implies xi minus 1 to xi cos nx dx is less than equal to 2 upon n. Okay. So this implies summation I goes to 1 to L f x I minus 1 x I minus 1 to x I cos nx dx. This is less than equal to summation I goes to 1 to L f x I minus 1 into 2 upon n. So 2 upon n will come out. So this implies summation I goes to 1 to L f x I minus 1 x I minus 1 to x I cos nx dx is less than 2 upon n. Summation I goes to 1 to L f x I minus 1. Okay. So let's say this equation number, last equation was 3. So let's say this equation 4. By Archimedean property of real numbers, we can find capital N belongs to N such that 1 upon 2 upon n summation I goes to 1 to L f x I minus 1 is less than epsilon by 2 for all n greater than a capital N. Because this part is fixed and 2 upon n, then n tending to infinity, this is tending to 0. So by Archimedean property of real numbers, we can find, okay. But we can use another argument that will be better. I am using that here. It will be better. No problem. Since 2 upon n summation I goes to 1 to L f x I minus 1 tending to 0 as n tending to infinity, thus we can find n belongs to n such that this happens. Okay, because n tending to infinity, this quantity is fixed. Summation quantity is fixed. This summation is fixed. This part is fixed, and n tending to infinity, it is tending to 0. So we can find this happens. Okay. Now let's say 5. Okay. So this is 5. This is 5. This is 3. Okay. From 2, 3 and 5. From 2, 3 and 5, we have the absolute value of IN is less than epsilon by 2 plus epsilon by 2. Because IN is less than the part, 2 summation part. Each summation part is less than epsilon by 2. Okay. For all n greater than capital N. So this implies IN is less than epsilon for all n greater than capital. So given any epsilon greater than 0, there exists capital N below n such that IN absolute value is less than epsilon for all n greater than equal to capital N. So this implies limit n tending to infinity, IN is 0. What is IN? IN is nothing but that integration a to b fx cos nx dx is equal to 0. Okay, so we have shown that this is 0. Similarly, we can show that. So we have shown that this is 0. Similarly, we can show that following the same process, we can show that this integration limit n tending to infinity a to b fx sin nx dx is actually 0. So Riemann-Lebesgue lemma is proved now. Okay. So thank you very much for today's lecture. If you have any problem related to this lecture, you can comment on my YouTube channel. Like, share, comment, and subscribe on YouTube channel. Thank you very much for today's lecture. We will see you in next lecture.